מישהו כבר אמר שהמצלמה שלך מאוד מטושטשת, דימה?
זה לא שלי, אין פה מצלמה שלי, שלי הוא אייפד.
אבל זה נראה שאתה לא בפוקוס בכלל, או שמשהו על הלנס של המצלמה שמצלמת אותך.
אוקיי, שנייה, צריך לנקות אותה.
לא נראה לי, זה לפי דעתי הפוקוס.
לא, כי בהתחלה זה היה בסדר.
זה פשוט לא בפוקוס כנראה.
מישהו, אני יכול להזיז את זה קדימה אחורה.
יש מצלמות שעושות פוקוס אוטומטי, אז תנסו אולי לנופף למצלמה. הנה, זה עכשיו בפוקוס.
אוקיי.
כן, הכל בסדר עכשיו, תודה.
אחלה. אז יש לך גישה למצלמה?
לא, אבל אני... אז אני מדברת עם יוסי על זה.
הבנתי. Okay, so let's go back to where we stopped last time. And today we'll play where did we stop? Just a second, I think I jumped. I think we stop here, yeah. Okay, so we'll play this Cauchy theorem for a bit more. Okay, and see what can we. Just a second. Okay, new share. Okay, so probably try to do it again. Share. Okay, maybe the same problem again. I need to what now? זה היה פה, ואני לוחץ על screen mirror again, ואני zoom user. Okay, better. Okay, and now, okay, hopefully we're in business. Hopefully we're in business. It looks slightly different than before, but okay, so we yes, I did. Okay, so let's play again. So I just remind you that we discussed functions on the complex plane, and we mostly focused on the functions with very simple singularities, namely poles. And we formulated a theorem, which was a Cauchy theorem that says that if there is a contour C on a complex plane, and we are computing integral dz of a function f of z along the contour C on the complex plane, that this thing will be 2 pi I equal to 2 pi I times sum over all points where the function f has poles inside the contour of integration. So let's label them k, and I write that these are poles of f inside the contour C, and there will be a sum of residue of function f at these points. So zk are poles of function f inside C. So I sum all the poles. So So for example, here there are several points. And I compute residue at each and every pole, sum, and this is the integral. This is the value of integral along the contour of integration C. That was the Cauchy theorem. That's probably the most important theorem of this course and most useful theorem of this course. And most of what we will be using in this course follows from this theorem in one way or another. And so this is it's a working horse of complex analysis. And I think you've started exercising this with Yoni and also at home. We'll practice with this a lot. Okay, so now let me discuss a variant of this theorem that may be useful. It has some practical implications, but it also connects the field of complex analysis to another branch of mathematics, which is called topology. It's a very simple connection, but nevertheless, it's a very nice one. So let us discuss an analytic function f. Function f of z, which is analytic in the domain D. And let's discuss a logarithm of this function. So there is a domain D on the complex plane. There's a domain D, and function f is an analytic function in this domain. So what we have constructed, we took the function f of z, and we computed a logarithm of this function. So for example, if the function is just example of, to make sure that everyone follows. So if f of z is z square plus 1, then we would be talking about logarithm of z square plus 1. This will be a logarithm of f of z. So that's roughly the construction. Then let's do one more step and compute a derivative d over dz of logarithm of f of z. So we first took a function f, analytic function in some domain, then computed its logarithm, then we computed derivative. What is the derivative of this complex function? Can anyone tell me?
F tag over f of z.
So this is the derivative of this function, yeah? Okay, cool. So let us now think about some simple function f. Just as an example, let us think about some function f of a that has a pole at the point a, the point z equal, sorry, take it back. Let's take a function f of z. Let me write it in words. Let's take a function f of z such that f of z equal a is 0. So this function vanishes at point a. So in other words, f of a is 0. An example of such function f of z is z minus a. Yeah? So let us look at what happens with the function z minus a, and then we'll try to extend our understanding. So for now, we can just think about this very specific function f of z equals z minus a. Later on, we will extend it to any function that vanishes at the point z equal a. And let's compute an integral along the contour C of this thing, d over dz logarithm f of z. Now, for this specific example, this will be equal. So far it's not specific. This is just the logarithmic derivative. But now, for this specific example, the derivative of function f of z is equal to
1.
1, correct? And f of z is equal to z minus a. So if there's this function that on the complex plane, there's a point A, so this is a complex plane Z, there is a point Z equal to A, and if in the complex plane there is an integral, there is a contour that encompasses this point, then what can we tell about this integral?
Can you explain the last equation?
The last equation?
Yeah. How did you get from? Okay, no, never mind. You took
Okay, so we understand that. So what is this integral?
residue.
Yes, this integral this is a function that has a simple pole. We need to compute the residue of this function at the point A. What is the residue of this function? 1. So the integral is equal to 2 pi I times 1. So what have we learned? We took a function z minus a, function z minus a had a simple 0. Notice 0 at the complex plane, it vanished. And now I computed the integral of its logarithmic derivative, and I got that this integral is equal to 1. Now let us extend this a little bit. Let us take the function, and instead of function z minus a, let's multiply it by some number. Let's call it c1. So this is our new function. And I'm computing the same integral. So what will be the derivative of the new function, bf prime? It will be c1. What I will have in the denominator? I will have function f of z, which is now c1 times z minus a. But now I notice that c1 and c1, they are canceled. Therefore, if I have a function which is any constant times z minus a, then nothing changes. Now, let us think about some more general function. And the only thing that we know that this function vanishes at the point A. And I wanted to vanish linearly. Let us discuss only functions that behave as c1 times z minus a near the point A. So it means that I can add to this function any term that looks like c2 z minus a square, and so on. So near the point z equal a, the behavior of this function is essentially this. So what it means that the integral c dz f prime of z divided by f of z will be integral. See, here will be c1 plus 2c2 z minus a, c1 z minus a plus c2 z minus a square. Correct? dz. Now,
Why did you do only the two first terms and not this?
let me just keep the first and then in principle there are infinitely many. So then I looked at this integral and I said, okay, so the integral is c1 divided by c1 z minus a plus c2 z minus a square plus plus 2c2 z minus a divided by c1 z minus a plus c2 z minus a square, and so on and so forth, dz. Now, let us consider the first term. What is written there? It's an integral over dz, c1 divided by c1 z minus a, open the brackets, 1 plus c2 divided by c1 z minus a plus. Correct? Then I can cancel c1. And we see that this thing by Cauchy theorem must be equal to residue of this function at the point z equal a, which is 2 pi I, because none of these terms contributes, they all vanish at z equal a. Now, if I look at the second piece, I realize that the pole z equal a is a regular point. There is no singularity at this point, and therefore this thing yields 0. Therefore, if I take any function f of z that behaves near z equal a as linear function, we will get that the integral of its logarithmic derivative is just 2 pi I. Okay, now.
But if you can go down a little bit.
Down is there?
Yes.
Okay.
You told that the second term is equal to 0, but if you take z minus a, it's not 0.
I don't get it.
There is a singularity in the z equal a.
No, at the point z equal a. Okay, so let's okay discuss the second term. So second term, it's an integral over dz, z minus a divided c2 z minus a, c1 z minus a plus c2 z minus a square plus. So let me cancel 1 power of z minus a, so it's integral dz 2c2 divided by c1 plus c2 z minus a plus. So now, so there is some point A, and let me take a small circle about this point. Now, near the point z equal a, all these terms can be neglected. And therefore, this integral is approximately equal to integral along the contour C dz 2c2 divided by c1. But this is just a constant times an integral on a closed trajectory along dz, and this trajectory can be shrinked into a point, and therefore this integral is equal to 0. So what have we learned? We learned that if we have function, any function that vanishes at the point z equal a, and the 0 is of the first degree, namely it vanishes linearly, then the integral over its logarithmic derivative is equal to 2 pi I. Now let's see what happens if the function has a 0, but this 0 is of nth degree. So it's z minus a in the power n plus high order terms. So to be very, very specific, just as an example, as the simplest example of this type, let's consider f of z equal to z minus a in the power n. Cool.
I have a question about the previous. Can you scroll up a little bit? No, when you canceled a little, yeah, you canceled the z minus a.
I neglected it. I didn't cancel it. I neglected it. Oh, you mean this here? Yes, this line.
Yeah.
Okay.
And then,
yeah.
okay, so okay, I'm okay with I'm okay with canceling. But why did you say that the rest is 0? The C2 and on and on.
So so there's a point on the complex plane, the point A. I'm in the vicinity of this plane, of this point. So I can approach, I can make my contour of integration as small as I'd like to be. So z minus a. So I'm saying that term z minus a times any constant is much, much smaller than C1. Because I'm integrating around this point. So I can change my coordinates, call z minus a my new coordinate, and make an integral along the contour, which is in infinitesimally small circle.
Okay, I see. Yeah, okay.
Okay, so now let's play with another example. So now take a function that also has a 0 at the point z equal a, but this time this is a 0 of nth degree. Yeah, so for example, if n equal 1, it's a 0 of first degree. If n is equal to 2, it's a 0 of second degree. If n is equal to 10, it's the 0 of 10th degree. So it shows the leading term in the vicinity of the point z equal a. The logarithm derivative of this function will be, so what is the logarithmic derivative of the function? Okay, correct. So let us check it. So let us check it. So this is df over dz divided by f of z. So this is n z minus a in the power n minus 1 divided by z minus a in the power n. And this is n divided by z minus a. Therefore, you can probably see it by now that integral along the contour c dz d over z ln f of z in this case will be equal to n times 2 pi I. So the conclusion from here that if we have a, now we can of course go back and generalize it and consider any function, not just the function z minus a, but just repeat the same steps we did before. Say that this is the term that of the expansion, essentially take this thing, yeah, and plug it back into Cauchy theorem. And then we will see that Cn will cancel, all other higher terms will be irrelevant, and this statement holds for any function that has nth order are 0. So this will hold for any function f that has a pole, a single pole inside C of the order n. Okay, so once we understood what happens with poles, let us see how sorry, with zeros. Oh, I'm sorry, I'm terribly sorry. Totally wrong. Forget it. That has a zero. That has a zero inside C of the order n. Not a pole, a zero. So function f of z, it did not have a pole at all. It only has a zero of the order n. So once we sorted out zeros, let us check what happens with the poles. So the story with the poles is very simple. So we all know what happens. We all know what happened. What we should do, we just write, let's write f of, as an example, z is equal to z minus a. Then the logarithm derivative of this function, f of z, would be f prime divided over f, which in this case will be minus 1 over z minus a in the power 2, divided by 1 over z minus a, which means multiplied by z minus a. So all this will be minus 1 over z minus a. So the only difference here between function that has pole and the function that has zero is the minus, is overall minus sign. And therefore, if we will now compute an integral dz along C of the logarithm derivative of this function, we will get minus 2 pi I. So, and similarly, if we will consider a function f of z, which has a pole of n degree, then its logarithm derivative will be minus n divided by z minus a. And therefore, the corresponding residue of logarithm f will be minus n. And the integral along contour C of dz, d over dz logarithm f of z will be 2 pi I times minus n. So what do we learn from here? Conclusion. Pole of the order n contributes to the integral are a contribution minus 2 pi I times n, 0 of the order okay, let's give it a name. P contributes a contribution 2 pi I k. So now imagine that we have a function. If we have a function f of z that has a pole of the order n and a 0 of the order p inside C. So we have a contour of integration C, and there are two points. There's a point, I don't know, W, and point psi, and here this point is a zero here is a zero of the order n, sorry, zero of the order p, and here there is a pole of the order n. What will be the value of this integral?
0.
So it's an integral along c dz d logarithm f of z over dz. So there are two singularities of the logarithm. Say it loud. Correct. So 2 pi I, and then just one needs to be very careful with signs. So 0 comes with a plus sign, and poles come with a negative sign. Yeah. So this is the degree. This is the degree of the 0 minus the degree of the pole. And notice that it doesn't matter where the point W and the point Xi stand. As long as they're inside the integral, you can take this point, you can shift it, you can move it. It does not affect the integral. You don't care what is the coefficient of the function in front when it approaches these points of singularity. The only thing that is important for this integral is the degrees of these singularities. Now imagine that we take this thing and we generalize it further. So let's imagine that we have a function that has several points. So we decided to call n what n was a pole, yeah? Just to be consistent, pole of the order. So imagine we have a function that has several poles of different degrees. So this will be points a1, a2, a3, a1, a2, a3, a4, and so on. So these guys are poles. Sorry, these guys are pole we call n. Okay, these guys are poles. So these are singularities of this function where function behaves as, so at the point a1, the function behaves as z minus a1 in the power n1 near this point, and so on. So these are set of singularities, of isolated singularities. Each of them is a pole of some degree. And there's another bunch of points, let's call them B1, B2, B3, and so on. And what was another index? And these are the zeros of the function. Which means that at point B1, say the function behaves as z minus B1 in the power P1. At the point B2, it behaves as z minus B2 times B2, and so on.
Can you explain the difference again between P and N?
So here's the difference. P is greater than 0, N is greater than 0. So N.
No, N is less than 0.
No, we assume that N and P are integers greater than 0.
Okay.
So at the point A1, function behaves as 1 over z minus a in the power n. And this is pole. Function diverges. At the point A1, function diverges. at the point B1, function converges and approaches 0. So these are zeros of the point of the function f of z. So these guys zeros. These guys are poles. So there is a collection of poles inside the contour of integration, and there is a collection of zeros inside this contour of integral. And now the statement is that if we compute integral along the contour C of the logarithmic derivative, what would we get? Your conjecture of the answer. Okay, it's 2 pi I, correct. Then the sum of all zeros minus sum of all poles. If I'll denote this number by P capital and this number by N capital, I will get 2 pi I P minus N. So this number, is the sum of the zeros minus the sum of the poles. Now, if I look at the left-hand side of this equation, so now let us discuss the left-hand side of this equation. Integral over dz of, sorry, I forgot the most important thing, logarithm. If I look at the left-hand side of this equation, what is it equal to? So the left-hand side of this thing, yeah? So let me write it again. So it's an integral over dz, d over dz logarithm of f of z. Let us discuss what is this structure. So this is the integral along the closed loop C. So if the loop would not be closed, if the contour C would be just any contour C, what is this thing?
0.
How do you know?
Actually, no, it's not. It's just f dz, right? Because it's not, yeah.
So this thing is essentially, if I do it very schematically, integral along C, d logarithm of f of z. Isn't it? If I'm allowed to cancel. So I have a contour of integration that I call C that goes from the point, I don't know, starting point. How do you call a starting point? Let's call it A, to some final point B. So I have a contour of integration, sorry, a curve of integration C. I just opened that. So I'm integrating along this curve from the point A to point B, the function which is logarithm f of z. What is this integral? Correct. So this is ln של f of a minus ln של f of b. Right? Just by construction. Sorry, yes, you're right. So let's change the sign. Correct. So what happens? What happens in this thing? What happens in this thing when I close the contour of integration? I consider it as a loop. So now I remember that my contour of integration was a loop. And I'm integrating from this point all the way up to itself. What does it mean? What does it mean now that I'm integrating dz d over dz logarithm f of z? With the understanding that we acquired above, that was a logarithm. So here it was a logarithm of the final point minus logarithm of the starting point.
If they're the same point, then it's zero, basically. If there's no points of singularity.
But there are points of singularity. So what is special? What is special with the function logarithm of z? So if I would be integrating, along the same contour z, d over dz, some function, I don't know, z, d. If it would be this integral, yeah, along the contour c, then this integral will be indeed zero, because you have integrated function. You went along this integral. You came to the function z. So this would be z at this point minus z at that point. And it will be the same function, and therefore you will get zero, or the same for z square or in exponent z. But here something special happens. Remember, we discussed that the logarithm is a multivalued function. So when we talked about logarithm for any function f of z, we said that logarithm is a multivalued function. It's actually a logarithm of the absolute value of f of z plus I argument of f of z. So when we say that there is a logarithm of z, that from the point of complex analysis, this is a function that has infinitely many values for any z. So let us be very, very specific. Let us consider the simplest example. F of z being equal to z. So that's the function, that the simplest function you can possibly imagine. And let's compute an integral along the contour c of dz d logarithm z over dz, which is an integral along c d logarithm z. So like you said, it's the value, it's the logarithm at the starting point, sorry, at the final point, minus logarithm at the final point. So let's denote this to be a starting point, and just to exaggerate the difference, that will be the final point. And let's describe z as e in the power I phi. Let's move on the circle of any radius. So let's call it r in the power I phi. You can set r to 1 or to any number. It does not matter. So from what we said, this should be a logarithm of a final z. So final z is this point. So what is this point? It's e in the power, what is equal to phi at this point? What is the value of phi at this point?
Almost 2 pi.
Almost 2 pi. So it's 2 pi I times r. Minus logarithm at the initial point. What is the initial point?
Ln r.
Ln r. And phi is equal to 0. So now let us compute this. So it will be ln r. Let me compute this logarithm. So it's the logarithm of absolute value of this function. This is logarithm of absolute value plus the argument. What is the argument?
2 pi I.
Plus 2 pi I minus logarithm r. And I add up with 2 pi I. So what did I do? My point z moved along the circle of I don't know, of radius r. And I fixed the value of its argument at the beginning, and I decided that let's call this point. It would not matter where I start. But I started at this point, and let's choose the value of argument. And argument is a multi-valued function, yeah? Let us decide that we start from the value of the argument and it's set it to 0. Now, let us follow how the value of argument changes as we perform a rotation. So we see that as we complete a cycle, as we complete a single cycle, the value of argument changes by the value which is equal to 2 pi. And therefore, we see that the logarithm derivative, the integral of this thing, is 2 pi I. So if you go back and look at our theorem, let's take the 2 pi I and move it and divide this equation by 2 pi I. Huh? So then what we get here is 1 over 2 pi I equal p minus n. Therefore, what we see from here, that 1 over 2 pi I integral along the contour C dz logarithm f of z is equal to 1 over 2 pi, the change delta of argument of the function f of z or along C. So in the example above, we took a function f of z being equal to z, we performed the contour of integration c was like this, and the argument of the function, the argument and the argument of the function was 2 pi. And therefore, what we saw, what this theorem is telling, that this is equal to 1 over 2 pi delta of argument of the function f of z. In other words, probably more geometric, we have function f of z, and function f of z has a real part and it has an imaginary part. So let us have a vector that consists of two components: real part of the function f of z and imaginary part of function f of z. In our example, where f of z is z, this would be r cosine phi, r sine phi. Z is equal r e I phi. So we have chosen the contour of integration to be a unit circle or circle of radius r. It would not matter. It can be any other closed curve that encompasses 0. So what do we do to compute the change of the argument of the function f of z? So let us first of all look at the simplest possible case, a unit circle, and we move along the unit circle. How did we compute the change of the argument of the function f of z? So we looked at this vector, and we computed how many times this vector rotates around origin. So we started at the beginning, this vector was here, and at the end of the day, the vector also comes to this point. It goes like this and completes a single turn. So the change of the argument on the closed loop, on the closed trajectory, simply denotes the number of times the vector turns around the origin. So in our example before, the number of times was 1. So tell me, if I choose a function f of z equals z squared, and I want to apply this theorem that we proved above, which says number of poles minus number of, I take it back, number of zeros minus number of poles is equal to 1 over 2 pi change of the argument of f of z on this trajectory. So what would be the value of the integral of logarithmic derivative of f of z if f of z is equal to z squared?
There is 1 0 at z equals 0.
But this 0 is of what degree?
Of the second degree.
Correct. So number of the zeros including their degrees. So if you want, you can split this 0 into two. You can split point 0 into 0 plus epsilon, 0 minus epsilon, and look at it as two zeros that stay very close. So these are essentially two zeros hiding at the point z equals 0. Okay, so number of zeros is 2.
Is 2 now.
Number of poles?
0.
Correct. And the change of the argument. So the left-hand side, we see that the left-hand side is equal to 2.
Why the number of zeros is 2?
Because it's z squared.
So
It implies the number of 0, including their degree. So it'll be.
So there is R and minus R.
No. Okay, let me proceed and then I'll come back to this point, okay? So from the left-hand side of this, we know that number of zeros is 2, number of poles is 0, so the left-hand side is 2. And according to our topological theorem, this must be equal to the change of the argument of the function f of z in units of 2 pi. So what is the change of the argument?
4 pi.
Pi.
4 pi.
So it's like the argument goes up by 2.
So let us check this. Let us check this. So let us draw schematically. So there is a contour of integration C, and our point starts here and ends there. It's the same point, but it approached this point after completing from below, from beneath, after completing a surface. So now let's see what happens with the image of this circle under the function z squared. So I'm moving my point of integration here. And now let's see what z squared does to this point. So when I start here, and my starting point in my target circle is also there, because my starting point is the point is coordinates on the plane 1, 0, yeah, and it's mapped to itself. Now I start moving here, and let's say I came to this point. So this point is mapped to, so this point I is mapped to point I square. Where's the point I square?
Below, like -1.
It's -1, so it's mapped there. Then I go to the point -1, and the point -1
Goes back to 1.
goes back to 1. So I completed half a circle in my original complex plane, but I completed the full circuit on my image plane. So it means that I'm moving twice as fast on this circle that on my original circle. So I completed the half of the circle here, but z squared already made a full circle. So when I complete the circle here, this thing will complete 2 circles. Therefore, the argument of z square will change by 4 pi. This vector that I draw here, oops, if I will draw here a vector, this vector will turn around the origin not once, but twice. Therefore, in the units of 2 pi, this will be 4 pi divided by 2 pi, which be equal to 2. So we see that the left-hand side, לי אין בעיה, אבל יכול להיות שלמישהו יש, אני בטוח שיש המון בעיה. אוקיי, אז so what was I saying? On the left-hand side of this equation, the left-hand side of this equation is equal to 2, and the right-hand side of this equation is also equal to 2. So we can follow the evolution of the vector, which is argument of fz along the contour of integration c. It will be always a multiple of 2 pi because this contour is closed. So any vector on the must complete an integer number of 2 pi's rotation. It ends up at the same point, which means it will be a multiple of 2 pi. But the equation is what is the multiple? So in this case, this multiple is equal to 2. And what this complex analysis theorem shows that this winding number, this 2, is precisely equal to the number of zeros of the function f minus number of poles of the function f. So you can connect 2 objects one to one, and they must be equal. So you don't need to know anything about function f, but to know how many zeros and how many poles it has inside it. And then the difference will determine how many times vector f of z will turn around on any contour c that encompasses 0. And now notice that you can take the contour, we have considered just a circle, but we can take any contour, we can deform it. The theorem will still apply. There's nothing here that depends on the shape of this contour, as long as it's just a deformation of a unit circle.
אפשר לשאול?
Yeah, sure, anytime.
אם נגיד יש לי פונקציה z בריבוע חלקי z פחות a בשלישית.
אוקיי.
מה הכתבים כאילו עכשיו? מה קורה איתה?
Okay, so let's discuss this function. So this function has 2 special points. From our perspective, from perspective of logarithmic derivative. So we will be talking about the logarithm of this function, yeah? So for logarithm of this function will be 2 points that will be special. What points will be special for this logarithm?
Fs ו-a.
Correct. So there is a point z equals 0, which is 0 of the function. Sorry, 0 Fs. And there is a point z equal a, which is a pole of f. So good. Now degrees of poles and zeros. So z equals 0 is a 0 of what degree?
You have 3 poles of 8.
Yes, so degree of the pole is 3. Degree of 0?
2.
2. Do you know now how to count the degrees of zeros? Okay. So what it means that now number of zeros we said will be 2. Number of poles will be 3. This is under the assumption, of course, that point A, point 0, this is Z equals 0, and this is point Z equal A, is inside the contour integration C. So if both points are inside the contour of integration, then we are getting that 2 minus 3 is equal to minus 1. So what does it mean? About the change of the argument. עשינו סיבוב הפוך, exactly. So our image moved into the opposite direction. So here we were moving on the Z plane. On the Z plane, we were moving in a counterclockwise direction.
לא, במרחב Z הלכנו עם כיוון השעון, אז כאילו כשנעשה מיפוי, אז נעשה סיבוב נגד כיוון השעון.
And there we moved in the opposite direction. So here will be, this as far as I remember, this is the clockwise. So this is clockwise. And this is anti-clockwise. So Z moves in anti-clockwise and makes a complete circle in an anti-clockwise way. Function f of z that you just described, z square minus z minus a in the power cube. So the function, so the image of this thing, which is z square times z minus a in the power 3, that image moved one full turn, but in the opposite direction. So just let me give you another example. Let me take something simpler. F of z equal to 1 over z. That function will do exactly the same.
So there is 1 pole.
No poles. Sorry, no zeros. Sorry, no zeros.
1 pole.
One pole of the degree 1. Yeah. So it means that the number of zeros minus number of poles will be minus 1. And this is equal to the number of turns. This is equal to number of turns. Number of turns.
So
sometimes people call it winding number. How many times it winds. And this is equal to minus 1. So it means, and in this case, it's easier to follow. So Z moves like this. 1 over Z, what 1 over Z does, 1 over Z, and this is very simple, goes like that. Goes in the opposite direction. So when this thing completes one circle in anti-clockwise direction, this thing completes a circle in the clockwise direction.
If it will be minus 30 kilo, חצי סיבוב?
I didn't get it. Say what will be minus half?
אם יהיה כאילו, נגיד 1.5.
So function f of z, so let's start. Function f of z is equal.
לא, כאילו בתוצאה של ההפרשים ייתן לי נגיד חצי.
No, look, notice. It's a number of zeros minus number of poles. Number of zeros is an integer number.
Number of zero, number of poles.
It's always zero, is always integer.
Not an integer. It would be 3 חלקי 4.
No, it's these are two integer numbers.
Okay.
Number of poles is always some integer. Number of zeros is also always some integer. So the difference is always, it cannot be 1/2. That's the key thing here. That's the most crucial thing, that these are always integer numbers.
Okay.
That way, and also another thing which is always integer, it's the number of turns. If you end up being at the same point, and you have to end up in the same point because you complete a full rotation, you must be in the same point. So if you come up to, you wind up being at the same point, it means that you completed an integer number of turns. It cannot be half of the turn. It can be say half of the turn. It must be an integer number of turns. It can be 10, it can be -1, it can be 0, but it cannot be fraction. It must be an integer number. And now this theorem states that these two integer numbers are identically equal. Number of zeros minus number of poles, including their degrees, is equal to the dividing number, how many times f of z are turned around. So in just another example to give you an idea, z in the power n, z completes, and the contour c, just a unit circle. So z completes one turn. F of z, how many turns f of z completes? Exactly. So if we'll follow f of z, it will be something like schematically, yeah? I'm exaggerating. So that will be n times. Now, if you look on the left-hand side, how many zeros, how many poles?
N zeros.
N zeros.
No
N,
poles.
N zeros, no poles. N minus 0 is equal to n. So it means, and here you see it geometrically, you see it very clearly, that this vector, if you follow the evolution of this vector, how it rotates, it clearly will complete n turns. So this is what this theorem says. And for the function z in the power n, it's of course elementary, but the statement is take any function which is analytic in this domain, compute this integral, and this theorem will always hold. Yeah, go on.
מה זה נותן לנו, אבל שאנחנו יודעים לעשות את זה? כאילו, למה אני צריך להשתמש בזה? כאילו, מה ה-use case של זה? זה אולי שאלה יותר...
You need to define, before discussing it, where will you need it in mathematics or where you will need it in physics. These are two different points. So probably there are some objects in mathematics and in physics that turn out to be very discrete. So there are some objects that you live in the world which is non-ideal. You compute an integral along some complicated curve. So for example, you take a curve, and let me try to do it. So you started with the function f of z. Function f of z completed z completed a single turn on the z plane, and its image performed just this funny motion that I completed. Now, so it's a complicated function, but then you will see there is a miracle here. You computed something very complicated. You got some very strange trajectory, and trajectory may look very differently, but then you will see that the result has not changed. So you'll see something which you add to this trajectory some wiggles that change the trajectory, they change the function, they change the trajectory without changing its winding number. Because by adding these wiggles, I didn't change the winding number. Therefore, I didn't change the value of integral. On the left direction of that equation, I might play with my function. I can change my function without changing its analytic structure. So I have some function which has the same number of zeros and poles. So I fix my analytic structure of this function, but I change the value of the function outside of these poles and singularities. So I modify the coefficients in front of the zeros and poles. So my function looks differently. So it's no longer z minus a, it's z minus a times, I don't know, 3. So naively, without this theorem, I would expect the results of my integration to change. However, because I'm not changing analytic structure of this function, what this theorem tells me and guarantees that the results of this integration will be unchanged. So it means that there are some mathematical objects that are only sensitive to the analytic structure, to the fundamental analytic structure of the functions, of the complex function. And they're absolutely robust, and you can change your function in many ways without changing its integral. And the manifestation of this behavior in physics, probably in mathematics, mostly in mathematics, but it has application in physics. So there are objects in this world that are magically robust to the details, and you perform some, I don't know, real physical experiments, and you end up finding quantities which are just in proper units are integers. And this miracle happens because there is underlying fundamental mathematical theorem that says that there are some integrals that just must be integers. So this is a manifestation of some topological properties in the complex analysis. So you use this mathematical construction, and you see there are some very fundamental objects that are on mathematical fundamental level are protected. Okay. Okay, people, I thought I will start the next subject today, but it looks like we are towards the end of this lecture. So I don't think it makes any sense to start anything new for 5 minutes, because no one will remember it in 1 week from today. So I guess I'll just stop here. And if you have any more questions that you want to discuss. If you don't, then go on, please. Okay, go.
אם יש לי Z בחזקת N, אני יכולה ללמוד שזה ענפים, כאילו, זה מחולק לענפים.
No, because z in the power n is a single valued function.
כן, אבל n יכול להיות כל מיני דברים.
Let's
n
pick
הוא לבחירה שלי, כאילו.
let's pick any n that you want. Let's pick an n.
שתיים.
Okay. Why doesn't it write? Interesting. It stopped. Is it because it got discharged completely? Interesting. No, I think it's no, it's okay. N equal to okay. So z in the power 2. So what are the branches?
לא, עכשיו אין לזה ענפים, כי קבעתי ש-n שווה ל-2. אבל אם לקחתי n שווה 3, אז הענף שונה מ-n.
No, it's a different function. It's still a single valued function, just a different function.
Okay.
It's not a multi-valued function. This is a single valued function. As opposed to square root of z, which is not a single valued function. Because there are two, so for example, you compute square root of 4, and you can say that either 2 or minus 2, because 2 in the power 2 is equal to 4, and minus 2 in the power 2 is equal to 4. So which one do you choose? Now that was your choice. You just decided I like more it to be positive, but you could have said I like more to be negative. That was your personal preference. Maybe not yours, maybe it was Euclid's, but that was a matter of choice. There were two functions that satisfy the same criteria, and you picked up one. But the function z in the power 2 is unique. So if you have 2 in the power 2, it can only be 4. It can never be, say, minus 4. Yeah? Okay. So, any more questions? Right.
להמשיך אתכן, אז נניח שדיברנו עכשיו על שורש Z, אז אני יכול, אז היא לא אנליטית, אז אני לא יכול להשתמש בקושי.
איזה פונקציה?
שורש Z.
מה זאת אומרת 3 כפול Z?
שורש Z, square root of Z.
Square root of Z.
Yes.
Okay. A shorter Z. Okay.
שורש, yeah.
Shorter Z. Okay. Okay. פונקציה f of Z. כן, פונקציה f of Z היא פונקציה רב-ערכית.
ולכן היא לא אנליטית, ולכן המשפטים של קושי כאילו לא תקפים.
ולכן כשאתה חושב על אינטגרל במישור Z, אתה צריך לבחור רק את הדומיין שבו אתה יכול להתייחס לזה כפונקציה חד-ערכית. כלומר, לחלק את המישור הקומפלקסי לאזורים שבהם אתה יכול לבחור ענף ולהישאר איתם.
סבבה. אחלה.
אוקיי. טוב, ביי.